So now let's talk about the sampling distribution of our estimators. So sampling distribution. In particular, we're just going to do the sampling distribution of beta hat 1. So that estimator beta hat 1. So let's first talk about the importance. So the first thing, we've already talked about with the appendix, we want our estimators to have certain properties. We want certain properties in our estimators. And if you remember, the two that we talked about, or two of them that we talked about in terms of finite sample, were unbiasedness. So this would be the idea that the expectation of beta hat 1 is the true value of that beta 1. And then finally, or secondly, I should say, I don't know if that's worthy of a finally, and the second one is that efficiency. So remember, that has to do with the variance of beta hat 1. So we're going to need to find the expectation of beta hat 1, and hopefully it's going to be equal to the true value, so we get an unbiased estimator. And the second thing we want to know is, we want to calculate the variance of beta hat 1, so we know if the variance is small, or we can compare it to other estimators to know if our least squared estimator is a good estimator. And the second reason why we want to get the sampling distribution is hypothesis testing. So we need to know the distribution of these estimators, because we want to be able to do hypothesis testing on them. Before we get started kind of deriving the distributions, we need to make certain assumptions. So the assumptions we're going to make is that the first one is it's linear in parameters, or our regression is linear in parameters. So this model maybe that we're currently using, let's pretend it's something simple like this. This is linear in parameters. So we're making an assumption here that what we're looking at, the parameters that we're looking at, come from a linear regression, or a regression that's linear in parameters. The second assumption we're going to make is that we have random sampling. So X and Y are IID. Independent and identically distributed, right? The value of one draw has nothing to say about the value of another one. The third one third assumption we're going to make is there's some variation in X. Essentially, we're talking about, so this X right here, maybe I'll put X1 to make it a little bit more clear. We can't have only one value. So like we couldn't run a regression if we had wages equals beta 0 plus beta 1 education plus U, and every person in our sample just had like a 12 years of education, like just had their just finished high school or something like that, then we couldn't estimate this relationship. So that's the third assumption. And then the fourth assumption, this is that big one that we've talked about before, is this expectation of U given, I guess X1 here, equals 0. So remember, this was a big assumption we were making. We did an example where we kind of did a regression that looks something like this one, and remember that in that U is ability and experience, and essentially what this assumption is there's no correlation between variables that affect wages and that are also in this U. So there's no correlation, between education and these variables in the U that also affect wages. So ability and experience, we might think they have an effect on wages, but we might think they're also correlated with education. If that's true, then this assumption fails. So this is a pretty big assumption here. Okay, so these are the assumptions we're going to work with. These are going to be our OLS assumptions up until now. And then let's start deriving these the distributions.